Welcome to a senior lesson for computer studies, and today we'll be looking at logic gates. So by definition, a logic gate is an elementary building block of a digital circuit. Most logic gates have two inputs and one output. Now, today we'll look at three logic gates, one of them being the AND gate. Now, there is a rule on every gate that is given. So the rule of an AND gate is that the output is true when both inputs are true. Otherwise, the output is false. So let's take note of the rule again. We are saying the output is true when both inputs are true. Otherwise, the output is false. So under logic gates, if an output is said to be true, it's simply denoted by a 1, and when an output is false, it's denoted by a 0. Now, as we look at this table here, we are seeing we have got, of course, the first inputs that are shown in input 1 and input 2. Those by default, that's the way they are put in the system or on the circuit. So input 1 we have got 0011, input 2 we have got 0101. That is the way it normally comes in. But let's pay particular attention on the output. Now, if you look at the rule in this case under AND gate, we are saying the output is true when the inputs are true. Okay? So in this case, if both inputs are true, then the output should be true. So if you look at the first table, the first entry, we have got input 1 is 0, input 2 is 0. Definitely there the output is false. Why? Because the inputs are false. Now we have got input 1 as 0, input 2 is true. In this case, they do not match with what the rule says, because the rule says the output must be true when both inputs are true. So the output definitely now the way it's showing there, it's 0 or it's false. It goes on. Now if you check down there where we have got input 1 and input 2, it shows 1 1, meaning both are true, meaning the output is also true. Now gates, they have got symbols. For this one, this is the symbol for an AND gate. Let's try to look at the other type of gate for today. Today we'll look at also the OR gate. Okay, so the OR gate also has got a rule. In this particular rule, you are saying the output is true if either or both of the inputs are true. I'll read that one again. The output is true if either or both of the inputs are true. If both inputs are false, then the output is false. What do we mean? Let's look at this table. Input 1, we have got a false input. Input 2, we have got a false. So what you're saying is, if both inputs are false, as you see in the first row there, it means the output is false. Why? Because the inputs there are false or 0 inputs. The second row shows input 1 as 0, input 2 as 1. So looking at the rule, we are saying the output is true if either, now in this particular case, in input 2 there is a true input there, so meaning it qualifies to be a true output. So we have got output as true. Thirdly, on the third row, so we have got input 1, we have got 1 true input, meaning the output would be true. Then the last row there, we have got 1 input and the other input 2. Looking at the rule, we are saying both of the inputs must be true, then the output is true. So that's how the table shows. Now let's look at the symbol for an OR gate. That is the symbol of an OR gate, and if you check closely, you see that the shape of the OR is like some kind of a symmetrical, but is different from the AND gate. All right, let's look at the other gate for today, which is the NOT gate. Okay, so the NOT gate also has got its own rule, where we are saying the output is false if both inputs are true. Otherwise, the output is true. Okay, look at this. So we are saying input, if an input is true, then the other one must be the opposite. Okay, so input 1, we are told is a true input, which means the output must be false. In this case, it says 0. Second row again, the input is 0, meaning the opposite of the input, it must be false. I mean, must be true, which is showing there. And there we have our symbol for a NOT gate. Okay. Now, how to work out logic gates in a truth table? Now, someone will be asking, say, what is a truth table? All right. Now, a truth table, by definition, is a diagram in rows and columns showing how the truth or false of a proposition varies with that of its components. Okay. So let's look at one activity for today and see how we can show the logic gates in a truth table. The question today, we are told to say, prove that A plus. Now, if you look at the letter A there, there's a small exclamation mark. Okay, that one in logic gates we call it as a NOT gate. So it's a NOT input there. In this case, we say not A. Okay, so prove that A plus not AB is equal to A plus B. Now, if you go back to a mathematical concept, you know that in an expression, when you are given, let's say xy, it simply means that you have to multiply. So we are given here A plus AB, meaning there is a multiplication which has to be done. So the question here, we are told, can you prove that A plus NOT gate AB is the same as A plus B using a Boolean algebra in a truth table? Okay, now let's look at the way this has to be done. So first of all, the question here says A plus NOT gate AB is equal to A plus B. So when you are entering inputs in this particular order, look at the number of letters you are given. That's what will qualify the number of inputs. In this case, there are only 2 letters that we are seeing. Well, there is A and B, meaning we only have 2 inputs of letters. So this is what will show. So like I said earlier on, if you check closely in the table A and B, the inputs, that's by default, that's the way they appear. So A, you have got a false, true, true. Then B, you have got the false, true. That's the way they are being put by default in a circuit. All right. Now, what it means in a Boolean algebra, NOT gate. If you remember what we did, what we looked at in the NOT gate. NOT gate is the opposite. So in this particular scenario, if you check on the first column there, where there's a false input, meaning the NOT gate of this particular 0, it will be a 1. So that's why we are given now a 1 there. If you check again in the column for A, because here we are matching with A, with the normal A, should I put it that way? Okay, I've got the NOT gate and the normal A. Okay, so in the first column there, I've got 0, meaning the opposite of 0, it's 1. The second 0, if you check the third row, where I've got 1, meaning in the NOT gate A, the answer will be a false, meaning it's a 0. And the other one, A, also there, it must be a false. Now let's look at B. Now for B, taking interest in this particular area, we are now multiplying the column for B and the NOT gate. We are using a Boolean algebra of calculating here. In this particular order, we are like multiplying now. So 0 times NOT gate 1, which is the truth there, we have the 0 there. 1 times 1, we have put 1. 0 times 0, we have got 0. 1 times 0, we have got 0. Okay. Now, what is A plus NOT gate AB? So in this particular scenario, we are going to look at the first column where I've got A0011, and we're going to multiply it with the NOT gate which you already got. Okay, should I say in column 4? Okay, NOT gate AB. So we will be matching the two by adding them. Okay, so if you check 0 plus 0 of the NOT gate AB, the answer should be 0. Okay, the 0 on the first letter A there, the second row that is, and adding it with the 1, we get a 1. Okay, let's go to A. A again, there's a 1. NOT gate AB, there's a 0. So 1 plus 0 is 1. Okay, in the letter A there, the last row, we have got 1. Okay, we are adding to the NOT AB, which is 1 plus 0 gives us 1. Okay, now on the last column there, we have got A plus B. Now, A plus B, we are going to add these two columns on the first two columns, A and the B. So 0 plus 0 gives you 0. 0 plus 1 gives you 1. 1 plus 0 gives you 1. And 1 plus 1 gives you 1. And now if you check the final answers, if you check A plus NOT gate B with A plus B, you realize that the inputs are actually the same. Boys and girls, thank you for listening.